सर
Good afternoon, everyone. Welcome once again to the Vertical One session. Today we have a very enthusiastic speaker, Professor Kunal Roy. This is his fifth lecture in the DDH training program. So I request Mr. Devabrata Das formally introduce Professor Roy before his talk. Please, sir.
Thank you, Dr. Himakshi, for giving me an opportunity to introduce our today's speaker. So our today's speaker is Dr. Kunal Roy. He is a professor and head in the Department of Pharmaceutical Technology, Jadavpur University, Kolkata, India. He has been a recipient of Commonwealth Academic Staff Fellowship and Marie Curie International Incoming Fellowship, University of Manchester, 2013, and a former visiting scientist of Instituto di Ricerche Farmacologiche Mario Negre IRCCS, Milano, Italy. The field of his research interest is quantitative structure activity relationship, QSAR, and molecular modeling with application in drug design, property modeling, and predictive ecotoxicology. Dr. Roy has published more than 300 research articles in referred journals. He has also co-authored 2 QSAR related books, edited 6 QSAR books, and published more than 10 book chapters. Dr. Roy is the co-editor-in-chief of Molecular Diversity, Springer Nature, and editor-in-chief of International Journal of Quantitative Structure Property Relationship. He also serves in the editorial boards of several international journals. Professor Roy has been recipient of several awards, including AICTE Career Award, DST Fast Track Scheme for Scientists, Young Scientists, Bioorganic and Medicinal Chemistry Most Cited Paper from Elsevier and Netherlands, Bioorganic and Medicinal Chemistry Letters Most Cited Paper from Elsevier, Professor R.D. Desai 80th Birthday Commemoration Medal and Prize 2017 from Indian Chemical Society, etc. Professor Roy has been a participant in the EU funded projects, nanobridges and nanotalks, apart from several national government funded projects like from UGC, AICT, CSIR, ICMR, DBT, DAE. With this brief introduction of our today's speaker, I request Dr. Roy to kindly start his lecture. Over to you, sir.
Thank you very much for the nice introduction, and good afternoon to all. Today's talk is on QSAR model development from small data sets. I've already given introduction to QSAR and calculation of different metrics of QSAR models, how to validate a QSAR model, how to define applicability domain of a QSAR model, etc. Now today we'll discuss an interesting aspect of QSAR model development from small data sets, because we encounter very often that the data set that we have for QSAR model development is very small. So there are some problems with small data sets for QSAR model development. So we'll discuss today on this matter. I will initially share some slides. Actually, I'll repeat some slides for recapitulation. So QSAR is basically acronym of quantitative structure activity relationship. These are predictive models which correlate the response property or activity or toxicity of chemicals with descriptors using some statistical tools. Now these descriptors are actually representation of molecular structure and or property. So these are numbers which encode information about molecular structure. So we can say that biological activity or the response property that we are going to model is a function of chemical structure and or property, or they are function of descriptors. QSAR is basically a ligand-based approach, so we have to start with the molecular structure representation, and then the information encoded within these structures are converted into numbers. And we have several columns here. Each column represents a particular descriptor. So we may have several descriptors, and one of the columns will be the biological activity column. Now, as we can generate a large QSAR table, so we have a large number of descriptors. So before applying any feature selection tool, we have to do data pre-treatment. That means some of the descriptor columns may be intercorrelated, and some of them may be having some constant values or very low variance values. So we have to omit those descriptor columns. So unless we omit those columns, we cannot properly apply our feature selection tool. So after we prepare our QSAR table, before applying the feature selection, we must do data pre-treatment, which removes constant value descriptors or intercorrelated descriptors, low variance descriptors. Otherwise, there may be some problem in the feature selection. So after we have treated the descriptor matrix, then we can apply a feature selection tool, and we can develop a model, which can either be a regression-based model or classification-based model. A model will be classification-based if our response is say binary type, say active or inactive, toxic or non-toxic. But if we have continuous values of response, then we'll go for regression. And our model will be able to calculate or predict exactly or precisely the response values from the developed model. And I've already discussed that there are several measures by which we can know whether the model that we have derived are statistically valid or not. They should have the inherent statistical quality in terms of, say, determination coefficient, correlation coefficient, variance ratio, standard error of estimate, etc. Additionally, we have to do validation test, because the usual metrics of the statistical measures, they do not give us any information about the quality of prediction. So we have to go for validation in terms of internal and external. And once the model is validated, then only we can apply it for prediction of new set of compounds after consideration of applicability domain. And also we can apply this model for design of new compounds, and for prediction of new compounds, and for mechanistic interpretation of the response property or activity being modeled. I've already mentioned that any QSAR should be developed based on OECD principles. The first principle says about the defined endpoint, where all the response values have been obtained using the same experimental protocol. According to OECD principle 2, we should apply an unambiguous algorithm. Every step should be defined so that anybody else can regenerate the model developed. So here the molecular structure representation, descriptor calculation, training set division, the training test division, then applying the feature selection tool to develop the regression-based or classification-based model or machine learning models, and prediction of tested compounds from the developed model. Everything should be defined. According to the OECD principle 4, we should also apply appropriate measures of statistical quality and predictive ability of the model. According to OECD principle 3, there should be a defined domain of applicability. And according to OECD principle 5, the model developed should have appropriate mechanistic interpretation. And that's why you should use such descriptors which have definite physiochemical meaning. As I mentioned, that validation is very much important, because when we apply any statistical technique, we will get some model, but it is important to know whether the model is applicable for the new set of query compounds or not, and what is the precision of predictions from the model. So validation is a tool by which we can know the prediction ability of the compound of the model developed, and the validation should be done using some prescribed methods of internal validation and external validation, which you will see in the next slide. The process of QSAR model development can be generally divided into 3 stages: data preparation, data analysis, and model validation. And validation strategies check the reliability of the developed model for their possible application on a new set of data. As I was mentioning that it can be majorly 2 types, internal and external. In case of internal, we use the same set of data which was used for development of the model either by leave one out or leave many out technique. And also we can apply bootstrapping and wide randomization. And in case of external validation, we apply a different set of data that has not been used for model development. So external validation is very important because here we are using some unseen data which has not been used for development of the model. So actually we are applying our model for prediction of data with some experimental response so that we can compare the predicted value with the experimental ones, and we can judge the goodness of predictions. And in general, the metrics for validations are 2 types. One is correlation-based metrics like R-square test, Q-square external F1, Q-square external F2, etc. And purely error-based measure like predicted residual sum of squares, root mean square error, mean absolute error, and so on. Now there is debate of internal versus external validation. One group of QSAR modelers believe that internal validation should be better if it is done in a proper way, because in this kind of validation we are not keeping some set of compounds aside for validation purpose, so we are not losing information. So one can do cross-validation in a proper way, in an exhaustive way. But in general, external validation is considered as the gold standard because we are applying some new. This we'll discuss in today's presentation. Now, as I mentioned that the currently accepted practice of QSAR modeling is to divide the dataset into 2 parts. One is training and another is test. And in case of small dataset, a significant amount of information is lost due to held out samples. In addition, if we are using the single training set of definite composition, there may be bias in descriptor selection, whatever strategy we apply for feature selection. In addition, if there are some potential outliers in the training set, in that case, that outlier may seriously influence the modeling of the data set. So data curation is very much important, especially for small data sets. In addition, I'll mention here that we can apply different strategies, especially for modeling of small data set. One is double cross-validation. Now, double cross-validation is a strategy where we can divide the training set into a calibration set and validation set many times, and we can redevelop the model based on the calibration set, and we can apply the model developed from the calibration set on the corresponding validation sets. And this we can do in several iterations. So in this way, actually, we can change the composition of the calibration set, and we can nullify the bias aspect, bias in descriptor selection. So in this approach, the validation is done in 2 loops. In the inner loop, the training set is divided into n calibration and validation sets, resulting in diverse composition, which are utilized for model building and model selection, while the test set in the external loop is exclusively used for model assessment. And as I mentioned, that this obviates the bias in descriptor selection due to fixed composition of the training set. So this is the scheme. The data set is divided into training and test in the usual way, but after we divide the data set into training and test, we can further stratify the training set into k-fold. So we get k number of calibration set and k number of validation set. So we will develop k number of models from k validation sets, and these k models are applied on the k number of validation sets, and we'll check the performance of the prediction of the validation set compounds from the models obtained from the k number of calibration sets. And we can then choose the optimal model based on different criteria, model with the least MAE value of the validation set, or from consensus predictions, or finding the best descriptor combination from the top models. So based on that, we can choose the best model and we can apply on the test set. Now, this is the scheme of double cross-validation. Now, we can apply this for the small data set also, where without dividing the data set into training and test, we can do only this thing, that is double cross-validation. And in that way, we'll not lose information in terms of test set. And we can do that is double cross-validation in an exhaustive way by generating all possible combination of calibration sets and validation set. So the details of double cross-validation we have published in this particular paper that is published in Cheometrics and Intelligent Laboratory System in 2016. The details can be found from this paper. Now there is another aspect. If we choose only a single model from a data set, then we have a fixed composition model that is a particular combination of descriptors. So that may again actually lose information. Instead of single model, if we have multiple model, if we can use multiple model, information from multiple model, in that case, we can use more number of descriptors in our group of models, and they can give sufficient information about the structural dependence or property dependence on the response, and that may give actually better performance. So consensus modeling performs better than individual models. And the strength of a consensus approach is that the final result takes into account the different assumptions of individual models, encompassing different chemical features and their contributions, allowing for a more reliable judgment in complex situation. And most importantly, the drawback of a single model can be nullified by another model used in consensus predictions. So consensus predictions are always preferable in comparison to individual models. So this is a scheme of consensus modeling. Actually, in QSAR literature, consensus predictions are done in most of the cases by taking average of predictions from multiple models. But in addition to this, we can do some intelligent consensus modeling where we can apply the concept of some qualified model. So this we'll discuss in detail here. Now, what is a qualified model? Now, to define a qualified model, now for each query compound, we have to identify separately 10 most similar training set compounds. 10 most similar training set compounds for a particular query or test compound using a distance method. And in this particular case, we have used Euclidean distance, using the combination of descriptors in each available QSAR model. Now, the 10 most similar training compounds will be selected based on structural similarity, and it may so happen that some of the compounds selected in the 10 most selected training compounds are structurally too much different. So we should have some criteria so that the 10 compounds selected are not much dissimilar from the query compound. So we should put some criteria here. So what is the criteria? The criteria here is the threshold value. The threshold value is the mean Euclidean distance plus k times standard deviation, where both mean and standard deviation are calculated using the Euclidean distance scores computed among all the training set compounds using descriptor values appearing in a particular model. So here we are using mean and the 3 times standard deviation. Actually, I have already mentioned if we consider a normal distribution pattern, mean plus minus 3 times standard deviation cover 99.9% of the population. So considering that, we are using mean plus 3 times standard deviation. If the distance score for a particular training compound is more than this threshold, that means that particular compound is too much dissimilar. from the test set compound, so we will not consider that particular compound. And in this way, if we see that actually we can select less than 3 number of compounds, similar compounds for a particular query compound, so it will be better to discard that particular model for prediction of that particular test set compounds, because for that particular query compound, there is not sufficient number of training compound based on which the model has been developed. So that particular model will not be able to predict well for that particular test query compound. So if the number of selected training compound is less than 3, then discard that model for prediction for that particular query compound. And if it is equal to or greater than 3, then the model is considered as qualified for prediction of the respective test compound. Now, in some cases, it may so happen that the distance score of the 10th compound and distance score of the 11th, 12th, and certain more compound is same. In that case, what we do? So Euclidean distance score values is same as that of the 10th most similar training compound, and X plus 1th compound has a higher distance score. So in such cases, we consider the X number of compounds instead of 10 compounds. So although we prefer to select 10 compounds, but if it so happens that the 11, 12, 13 compounds are having the same distance score as the 10th compound, then we will consider 13 number of compounds or X number of compounds, where up to X number of compounds they have same distance score as the 10th compound. Now, how we actually do the intelligent consensus prediction? It is of 3 types: CM1, CM2, and CM3. CM0 can be considered the ordinary consensus predictions, where we do the averaging of predictions as it is done in many QSAR literature. But in case of intelligent consensus prediction, we apply the concept of qualified models. So in case of CM1, we consider average of prediction from all qualified individual models. In case of CM2, we use weighted average predictions. And in case of CM3, we use best selection of predictions compound-wise from individuals. So we will discuss on this CM1, CM2, and CM3 now. As I mentioned, in case of CM1, what we do, we take the average of prediction, but only for the qualified individual models. So we have already defined what are qualified model. After defining qualified model, we will take predictions from the n qualified model, and that will be the average prediction from the n number of qualified model. So this strategy is actually important while considering the new query compound, because in case of dataset division, when we get the training and test set from the original dataset, in most of the cases, the tested compounds will have sufficient number of similar compounds in the training set. So in that case, CM0 and CM1 may be same. But in case of new query compounds, there may not be sufficiently similar compounds in the training set. In that case, CM0 and CM1 may not be same. Next one is CM2, weighted average predictions from all the qualifying models. Now, for a weighted average prediction, the average is computed giving an appropriate weightage to the qualified models for a particular test compound. So what we do for a particular model, absolute prediction error values of the selected training compounds are computed. I mentioned that for each query compound, we have to select 10 most similar compounds. And we have to see, based on the selected model, the cross-validated error, prediction error, leave one out prediction error. And absolute error value, prediction error value is considered. And we have to consider the mean of those absolute errors. So for each model and for each query compound, we will get a MACV value. So for n qualified model, the computed MACV value for a test compound are denoted as MACV1, MACV2, and so on. And if we take sum of these MACV values for n number of models, we'll get summation of MACV. And then we can actually consider relative fraction contribution of individual models from MACV1 by sum of MACV, similarly MACV2 by sum of MACV, and so on. And we can consider the weighted value as the reciprocal of this fraction. And then we can give a weightage for prediction from a particular model as the prediction value from a particular model into the corresponding weighted value. And in this way, we take sum, weighted sum. We multiply with the weighted value and then divide by all the weighted values, and we get weighted average prediction. So this is weighted average prediction for each query compound. And third one is CM3, that is best selection of prediction compound wise. Here we are not doing the averaging based on weightage. What we are doing, we are selecting a single model based on the MACV. So for query compound 1, it may so happen that model number 3 is the best model. But for query compound 2, model number 2 is the best model. So for different query compounds in the test set, we may have different models suitable for prediction. So here we are using multiple models, but for each query compound, only one model, and that may be different for different query compounds. So this is query compound specific. So this is consensus modeling 3. So now we have calculated predictions for different query compounds based on different methods of consensus predictions. So from CM1, from CM2, from CM3. So we have the corresponding predicted response values. And in a data set, for the test set, we have the observed and predicted values. Say predicted value obtained from CM1, predicted value obtained from CM2, predicted value obtained from CM3. And we can then calculate the different metrics in the usual way. And we can also calculate the MA test value based on different metrics, and we can compare them, that from which consensus models we got the better prediction based on MA. And we can also apply here MA 95%. I have already mentioned in my second class that one can use MA 95% to know the performance of a model for most of the compounds in the test set. And that is actually desirable. It may so happen for 1 or 2 compounds the prediction is bad, but for rest of the compounds is very good. So in that case, we can choose that model because it is doing well for most of the compounds in the query set. Now we can also apply some additional criteria, Euclidean distance cutoff, applicability domain, and Dixon Q test that may help in improving the quality of prediction for the query compound. So Euclidean cutoff, applicability domain, and Dixon Q test. These are the additional criteria which we can use here. So Euclidean distance cutoff. Now I mentioned that we will select 10 most similar training compounds, and we are applying some criteria there that the distance should not be more than the mean plus minus 3 times standard deviation. Still, we can apply additional Euclidean distance cutoff if we want to consider those training compounds, those which will be within some specific distance range. So one can set a Euclidean distance cutoff value, and these values are usually normalized between 0 to 1, to limit the selection only those training compounds with the Euclidean distance score less than equal to the user-defined cutoff value. Here, the Euclidean distance score calculated between a query compound and a training compound I is scaled using maximum and minimum distance scores computed for that training set compound I from all remaining training set compounds. So we compute the maximum and minimum distance scores of that particular training compound I from remaining training set compounds, and based on that we can actually score, that is normalize the test set distance score. So in a similarity scale, Euclidean distance score 0 means exactly same compound, whereas the distance score value increases with similarity basis, decreases. Distance score value will increase as the similarity decreases. Next, we can apply concept of applicability domain. As we know that when we are applying some model, the model should have the applicability domain for the particular query compound. So we can apply that, and we have applied here the AD using standardization approach. I've already discussed this in the last class. There are several methods, but we have applied here ADE using standardization approach. And third one is Dixon Q test. Now we are having, say, 10 number of training set compounds selected for a particular query compounds, and we are also calculating their leave one out prediction error. But it may so happen that some one or more of the compounds have a prediction error that is actually outlier. Outlier means which is sufficiently different from rest of the compounds, although the compounds are structurally similar. So to obviate this problem, we can apply the concept of Dixon Q test. So where we omit one compound from the other compounds, provided that the total number of compounds is limited, usually less than 10. So here we are selecting 10 number of compounds. So we can apply Dixon Q test. So presence of response outlier may lead to incorrect selection of the best model. So we apply Dixon Q test to detect and remove such prediction outlier. Now, if we have more than 10 number of training compounds selected for a particular test compound, as I've already mentioned that in some cases it may so happen that 11, 12 or 13 compounds are at the same distance score as in case of 10th compound. In that case, what we will do, we consider only up to 10 compounds, and the prediction error of those compounds, that is 10, 11, 12, 13 compounds, we take average of those. So in that way, we will consider up to 10 compounds only for Dixon Q test. One important point, as I've mentioned, that while applying Dixon Q test, care should be taken about the number of observations. As I mentioned that in some situations, the number of similar training compounds selected for a test set may be greater than 10. In such situation, we compute the average of prediction error of all the training compounds having the same Euclidean distance as of 10th compound. And in that way, we have only 10 compounds selected for the Dixon Q test. So after we have calculated prediction error using CM1, CM2, CM3 and applied the additional criteria, then we have the CM1, CM2 and CM3 predicted response values for all the query compounds. And we can then calculate different metrics for predicted values of the tested compounds. And we have also developed an open access user-friendly software, intelligent consensus predictor, which perform all these three types of consensus prediction in addition to the usual consensus CM0. This tool can be used to identify an appropriate set of optional criteria for prediction of newly designed query compound using training set models and corresponding test set. So this software tool is freely available from this site and this site. So details of the manual, how to give the input, what is the format of the input, these are given in the manual that is downloadable from the site. And some example files are also given. When you download the software, then in one folder there will be sample input file also, which help you to know what is the criteria for the input files. This is a GUI for intelligent consensus prediction, where you can select the training set models, then test set file, and select output file, and you can apply additional criteria like Euclidean distance cutoff, AD criteria, Dixon Q test. And value of K for the threshold can be actually changed. By default, it is 3. We've also done some case studies to know the application of intelligent consensus predictions. And for this purpose, we chose 6 data sets from toxicology, like toxicity of ionic liquids to bamboo fishery, from property odor threshold of wine components, from sweetness property of 240 organic molecules, from pharmaceutical data set, cycling dependent kinase inhibitors, then acetylcholinesterase inhibitor, and again property solubility of C60 in 156 organic solvents. So what we have done in each case, for each data set, we have divided the data set into training and test set in 3 different phases. One is sorted response, and the Skinner stone, and this modified K-medoids. And for these divisions, we have used our own tool that can be obtained from this site. In each case, we have divided the data sets into training and test using 70-30 ratio. Mostly we apply 70-30 ratio, 70 in the training set and 30 in the test set. Now, if your data set is very small, sometimes people use very small data set as test set, say 4, 5, 6 compounds, but test set should not be less than 10 compounds. And then we have applied variable selection and statistical model development using stepwise MLR, genetic method, GFA, and partial least squares. Now, in all cases, we have applied intelligent consensus prediction. So we have the predicted values based on CM1, CM2, and CM3 after application of different parameter settings like Euclidean distance cutoff, applicability domain, and Dixon Q test. And finally, we have the predicted values, and for all tested compounds, we have calculated the metrics, different kind of metrics like Q square F1, Q square F2, F3, and so on, and MA-based criteria. The details of these metrics can be found in standard literature, QSAR literature. And we have mainly applied the MA 95% value as a means of comparison among models. Why MA 95%? Because we can omit some compounds with outlier predictions, maybe showing very high residual only for 1-2 compounds. So we can nullify the effect of those limited number of compounds, and we actually evaluate the performance of the model for most of the compounds in the data set. So we prefer using MA 95%. Mean absolute error in predictions after omitting 5% high residual points in the test set has been considered along with other classical metrics. This has been done in order to prevent the influence of any high prediction errors that may significantly obscure the quality of prediction for the whole set. So we apply MA 95% for comparison. Now we see, now we compare the performance of the consensus models from the individual models. In each case, we have 5 individual models, and these are the MA 95% values for the test set. Now you can see among the 5 individual models, this is the model giving the lowest MA 95%. The error will be lowest for a good model. So among the 5 individual models, we have this lowest errors. So this model is the best among the 5 individual models. But when we apply consensus predictions, the CM2 actually gives a further lowering of MA 95%. So CM2 is the winner model here. In case of another division, Kenner-Stone, actually IM5 is the best model based on the MA 95%. It's showing the lowest error. But when we are applying consensus prediction, we can see the CM3 is the best model actually. It is further lowering the MA 95% value. Among the individual models, but CM2 further lowers the value. So CM2 is the winner here. In all cases, actually, the consensus models are winner. Somewhere CM2 and somewhere CM3. In case of dataset 2, similar pattern we see here for this particular division, CM3 is the winner. For this particular division, actually there is a tie between the IM4 and CM3. And in this particular case, as you can see, the CM2 is the winner. Similarly for dataset 3, CM3 is the winner in comparison to the winner model, individual model. This 362 versus 0.4 of IM1. Similarly for Kennard Stone division, CM3 is the winner, and for K-meter division, it is CM2 is the winner. Similarly for dataset 4, we see CM2 here is the winner. For Kennard Stone division, CM1 and CM2 both are sharing the same value, but this is lower than IM4. And in case of K-meter, CM2 and CM3 share the same value, which is lower than IM1. Similarly for dataset 5 also, we see the consensus models are better. Actually, CM3 is better in all the cases here. Similarly for dataset 6, you can see the consensus models are winner. Now what happens from this 6 data sets? We can see that if we see the winner models, mostly CM2 and CM3 are the winners. So this is for toxicity data set, vivdo-officially toxicity data set, this is the water threshold data set, this is the sweetness potency data set. In some cases, CM1 also share, like in case of the cyclin dependent data set. This ACH data set, only CM3 is the winner, and in case of the solubility data set, CM2 50%, CM1 25%, CM2 25%. Now, if we see division wise, considering all the data set, then for sorted response, CM3 actually 67% versus CM2 33%. In case of Kennard Stone, it is CM3 50%, other two 25%. And in case of modified K-meters, CM2 is down in most of the cases, 71%, CM3 29%. If we consider all the cases, then you will see the CM2 and CM3 are 48% and 43%. CM1 is only 9%. CM1 is similar to the ordinary consensus predictions, but here we have used qualified models only. But overall, we can say the intelligent consensus predictions are better than the ordinary consensus prediction, and these are better than the individual model predictions. And this is the overall reduction in the MA 95% value on using the consensus modeling. This is for overall, and this is for different division pattern, and this is for the data sets, different data sets. So here, from this part, what we know that the consensus models can perform well in predictivity than the individual models. So individual models may not perform well in all ways. So if we do the consensus modeling, that can give a better prediction picture actually. And from this study, we saw the CM2 and CM3, these intelligent consensus predictions are actually the winners in most of the cases. Although the CM1 is similar to the average of predictions, but we have used here the qualified models. The other two are newly introduced here. So weighted average predictions and the compound specific selection of the model for CM3. Now here, in case of consensus modeling, actually reliability of predictions increases. Prediction of query compound is not biased because we are not using a single model. And prediction will consider weighted average predictions or compound wise prediction. We can apply the additional criteria like Euclidean distance cutoff, AD criteria, and Dixon Q test that gives more reliability. And consensus predictions are better than individual models because the individual models may be biased based on specific compounds predictions. So consensus is always better. And here we are actually increasing the quality of predictions using consensus model, but also we can increase our interpretability from the models. In a single model, there may be a limited number of descriptors, but when you are using consensus models, we are using more than one number of models. So we are using more than one set of descriptors. So that may help you in describing some physiochemical phenomena. So that should be taken into account. And one model actually may nullify the effect of the other model. That means drawback of the other model. So if some of the model has some drawbacks, that can be overcome using consensus modeling approach. So the consensus modeling in an intelligent way, this has been described in this particular paper in Journal of Chemometrics. So one can go through this paper for further details of intelligent consensus prediction. Now we are discussing these two aspects, double cross validation and intelligent consensus predictions for a small dataset modeling. So we again come back to our original topic, that is small dataset modeling. Today we are interested about the small dataset modeling where we have small data. Now what do you mean by small dataset? Usually if the number of compounds is less than 50, then we can consider a particular dataset as a small dataset. Now, as I mentioned that in case of small dataset, it is not advisable always to divide it into training and test because we are losing some information. So we can apply some other criteria, additional criteria. Now, what are the criteria? One can apply double cross validation, one can apply intelligent consensus predictions, and one can avoid the division of the dataset into training and test, but to apply the multiple or exhaustive double cross validation and do leave many out in an exhaustive way. So these tools are actually available in this site. I'll discuss more. Now here for small dataset modeler, we have also small dataset curator. Now after a dataset is chemically curated, chemical curation means removing mixture, removing inorganics, and converting a salt to corresponding acid or alkali form, and normalization of the representation of some functionality, etc. So we have to use the chemically curated dataset, and then what we have to do, we have to do dataset curation. Now in dataset curation, we have duplicate analysis, structural outlier removal, response outlier removal, and activity clips analysis. And then only we can use it for the final analysis. Now what are these? Now duplicate analysis means the same compound may be present in your dataset in more than two occurrences. So we have to identify those. And we can identify those based on the values of the descriptors. So when a given pair is found, if the experimental response values are identical, then there is no problem. We can retain one and omit other, keeping the same response value. But the problem arises when one of them is different from the other. In that case, if the value is not too much different, then we can keep one and consider the average of response values of the two compounds as the response value. But if the response values are significantly different means so much different that they can be placed in two different classes actually. So in that case, actually we can remove both of the compound unless there is a possibility to check that response value of which of the compounds is correct. Then outlier analysis, response range outlier analysis. Response range outlier means some of the compounds may have the response which is quite different from rest of the compounds. So in such cases, we can remove such compounds because it can strongly influence the modeling. Especially the correlation-based metrics will be highly dependent on such values because these are based on the range of the response values. So what we can do, we can use mean plus k times standard deviation. Usually k is 3. And mean and standard deviation values are computed based on the experimental response values of the compounds. Next is structural outlier omission. This is based on the calculated values of descriptors. And structural outliers will be those if the mean distance score is outside the range defined by mean plus minus k times standard deviation, where mean and standard deviation values are computed based on mean distance score values of the compound. So if for a particular compound the distance score is outside this range, that should be omitted because this is sufficiently different from rest of the compounds. And we have also to do the activity cliff analysis. Now what is activity cliff? Activity cliff means the compounds are sufficiently similar in their chemical structure, but the activity value is quite different. So this will be difficult to model because QSAR is based on the similarity approach. So when we are applying compounds with activity cliff, then the model cannot handle that situation unless we have some knowledge that why they are different. So in small data set curator, we can do activity cliff analysis based on the Euclidean distance score using some user-defined criteria. Now, based on the number of similar compounds, we can apply some criteria. If we have more than 3 number of compounds, equal or more than 3 number of compounds as candidates for consideration as activity cliff, then one criterion. If the number of compounds is 2, then another criterion. And if number of compound is 1, that means one compound is similar to the query compound, but having sufficiently different in the response value, then another criterion. What are the criteria? Now for criterion 1, that means when the number of similar compounds is more than equal to 3, then what we do, we take mean value of the similar compounds and compare with the response of the query compound. If the difference is more than the threshold, usually threshold is considered as 1, and if the corresponding p-value is less than 0.05, then there is a presence of activity cliff. If the number of compounds we are considering similar, there are 2. What do? We consider the mean of those similar compounds and calculate the difference from the response of the query compound. If this difference is more than the threshold, usually 1, and also the difference between mean and response is more than the response difference of the 2 similar compounds, then there is a possibility that the activity cliff is present. And in the third case, only one compound is similar, then we just see the difference between the similar compound and response of the query compound, and if it is more than the threshold 1, then we consider there is an activity cliff. And then after curating the data set, we go for small data set modeler. Now in case of small data set modeler, we apply exhaustive double cross validation, and we apply also the concept of intelligent consensus model. Now, as I've already mentioned, in case of double cross validation, what we do, if we have n number of compounds, curated compounds, and we consider r number of compounds in each validation set, so we will have k number of validation set. So actually, we can have very large number of combinations. So this is done in automated way. So we will have k number of MLR and PLS models, and then we apply this for prediction of the corresponding validation set. And we can actually select the best model based on some criteria, like least MAE 95% value of the validation set, or least MAE 95% value of the modeling set, or modeling with model with highest Q square LM out, leave many out of the modeling set, using some pooled descriptors of the top 3 models based on the MAE 95% of the validation set. In case of MLR, we can do best descriptor combination, and in case of PLS, we can use pooled descriptor model, or you can use the consensus, simple consensus modeling or weighted average prediction based on the top 3 models. So there are several options actually. So small dataset modeler implements exhaustive double cross validation. In the inner loop, the modeling set is repetitively split into calibration and validation sets. As we are dealing with the small size modeling, say n number of compounds, the best way is to derive all possible combinations. So this may be a huge number of combinations if your number of compounds is very high. But if it is small number of compounds, so we can do so. Small means 50 or 100. And we can apply different methods like genetic algorithm MLR or GAPLS. And we can calculate our usual metrics for internal validation like R square, Q square, LO, Q square, LMO, MAE, LO. And for external validation, Q square external F1, Q square external F2, and Q square external F3, and so on. And MAE 95%. And this we do for both the inner loop and outer loop. And the software also calculates the corresponding PLS models for each MLR model generated. And I have already mentioned there are 5 ways of selection of model based on the lowest MAE 95% in the validation set, or MAE 95% of the modeling set, or highest Q square LMO of the modeling set, or top ranking models based on the MAE 95% values in the respective validation set, or the unique descriptor appearing in the base models. We can use those base descriptor combination for MLR, and for PLS we can use the pooling. So we have done some case studies using 7 different data sets, using some QSPR and QSTR and QSAR data, some solubility data set, short-term toxicity to Daphnia magna, this is for predictive toxicology, reported acute toxicity to some fish, nitrated polycyclic aromatic hydrocarbons with reported mutagenicity data, toxicity value to pseudocrystalline subcapitator, then cyclic sulfone derivatives as base 1 inhibitor, anti-Alzheimer, and also cycling-dependent kinase inhibitors. So 7 data sets. Now in the seventh data set, the data set is quite high. There is large number of compounds are there. So here, what we have done, we have done several divisions actually. Initially, in each case, we have kept some compounds at the external set. So from 49 compounds, we have kept some compounds at the external set just for the sake of our validation purpose, validation of our strategy. So we have kept some compounds out, and rest of the compounds, for the rest of the compounds, we have applied our strategy. Now we could have used the whole set, but in that case we could not prove that what is the application of our strategy. So just to prove that, we have kept some compounds aside. So in each case, we have kept some compounds aside. Now in this particular case, in the 7 data set, we have kept some compounds aside, and then the rest of the compounds we have again divided into several smaller sets to increase the number of sets actually. So the original data set is divided into 2 parts. One is true external set, which is never used in any kind of modeling analysis. This is used at the end of modeling. And the small data set that we are getting. So small data set we are getting from here actually. Then we are applying 3 strategies. One is the holdout method. That means again division into training and test in the usual way, what people do. Then whole data set modeling without division of any training and test. We are using the whole set, and then the proposed approach of double consolidation. So 3 different ways. So in this case of holdout and whole data set modeling, we apply the genetic algorithm method for variable selection, model, and we select the final top models. And for our proposed approach of double cross validation with some optimal model selection criteria, including consensus predictions, we get the predictions. And then we compare the predictions from all these models from the external set that we have kept aside here. So this comes here. So we see what is the quality of prediction in terms of MA 95% value. This we will show here. In case of data set 1, as you can see, in case of whole data set, the MA 95% of the external set is 0.611, and in case of holdout classic approach, it is 0.576, somewhat increased. Next, we have used our approach. One is without data curation. Here, the curated values, some of the values are actually lower than this. But more interestingly, if we apply data curation means, as we have already mentioned, that removal of structural outliers, removal of response outlier, removal of activity cliffs, etc. In that case, we can see there is significant improvement in the MA 95% value. So in several cases, we are getting 0.315. In the previous case, the lowest value was 0.576 from the classic approach, and after application of this criteria, it is 0.315. That is obtained from different models, while we are getting different models here because we have MLR and PLS models, and the best model is selected based on different criteria. I have already mentioned that we have 5 different criteria. So we can see after application of our approach, the quality of prediction improves to a great extent for data set 1. In 2, you can see from the whole set we are getting 0.302, and from holdout approach it is much higher, 1.062, and these are the values after application of our approach, but without data curation. When we apply data curation, it becomes 0.133 from this particular model. As you can see, this is much lower than the previous one of 0.302. So our approach is helping here with the data curation technique to lower the prediction error for the external or query compounds. In case of data set 3 also, you can see this is from whole set 0.250, from holdout is 0.238, and when we apply our approach, it is becoming 0.146. Here, this without data curation. Actually, there is no activity cliff or outlier here. In this particular consensus model, we get much lower value of mean 90%. As there is no activity cliff, so there is no new result here. In case of dataset 4, as you can see, for the whole set is 0.595 and holdout is 0.789. And then we apply our approach here with this without curation and this with curation. As you can see, after application of curation, it becomes much lower, 0.357 compared to the previous one, 0.595 here. In case of dataset 5, as you can see, the best one actually from the classic approach is here 0.361, but when we apply our approach, it becomes 0.227, but this is without curation. Interestingly here, when we apply curation, then there is no actually improvement. So the winner model has been obtained without applying curation here. So this was one exception. In dataset 6, as you can see, this is classic approach showing 0.572 compared to our approach 0.467, much lower in terms of mean 95%. This is without curation because there was no outlier activity claim. In dataset 7, I told in dataset 7 there are 8 type of division. So I will discuss those. Now in case of division 1, actually the base model comes from classic approach. Instead of our approach in this particular one division, we get the best model from classic approach instead of our approach. This was an exception. In case of dataset 2, the best comes from this approach, consensus weighting average. In division 3, the best comes from here, consensus. In case of division 4, best comes from here, consensus. In case of division 5, best comes from here. In case of dataset 6, it comes from here. Pooled is dataset 7, division 7, it comes from here. And division 8, it comes from here. Here, sorry. Discussion actually is clear that in most of the cases we get the best model from the applying our approach of small data set modeling involving double cross validation and involvement of consensus modeling and application of curation, data curation. So this gives more consistent result. We have simply compared the prediction performance of the QSAR models that are obtained potential approach with the QSAR models obtained from our approach. So we have actually total 14 optimal models here from 6 data sets and 8 models from the 8 divisions of dataset 7. In 13 out of 14 cases, actually the optimal model was obtained from our approach. Only in one case it was obtained from conventional approach. And we got the best model from 6 MLR PLS models in 6 consensus model approach and 2 pooled approaches. And there is a crucial improvement of quality of prediction in case of dataset 1, 2, and 4 when we applied the data curation. So this is the graphical user interface for small dataset curator and small dataset modeler. And this is the our site, the JDView site, from where we can get different tools which can be downloaded free of cost for academic purposes and also for business purposes. And this is the site for small dataset modeling, where we will get the small dataset modeler and small dataset curator, and also the usual holdout approach. So this standalone software tool, small dataset curator and small dataset modeler, are available from this site. And this helps in duplicate analysis, response range, structural outlier detection and activity cliff analysis, which are highly recommended, especially for QSAR modeling of small data set, because as you have low number of compounds, if there are some activity cliffs or outliers within these small number of compounds, this will highly influence your modeling. So it is always advisable to apply curation, data curation, before you apply your model development strategy. Small dataset modeler software is designed to handle QSAR modeling of small datasets, and it provides functionalities including exhaustive double cross validation and optimal model selection for model development. We have also performed different case studies, as I have already mentioned, and which showed that the consistent results are obtained from application of our approach. And this work is available from Journal of Chemical Information Modeling, published in 2019. So one can go through this paper for further details. And to know more about different QSAR metrics, metrics for validation, applicability domain, and some fundamentals of QSAR, one can go through this text. Now, regarding the drug discovery hackathon, these are the two sites which one can use for QSAR model development and different small tools like data pre-treatment and variable selection, doing PLS and doing double cross validation, consensus modeling approach, and the external prediction using different metric calculations like Q-square, external F1, F2, and so on. I have got some query how to calculate Q-square, external F1, F2, etc. So for that, I can say that in the drug discovery hackathon original site, there is one guideline document. In that guideline document, there is also guideline for QSAR model development. So you click on that particular guideline for QSAR model development, and inside you will find some links, and some study materials are also given there, which discusses on the calculation of different kind of metrics, how to do the applicability domain, how to check applicability domain, and about how to use the software tools, what is the criteria for input files, and so on. Okay, so you can go through these sites, you can explore these sites. These are freely downloadable. If you have some questions related to QSAR model development, you can ask. Thank you very much.
Thank you, sir, for your informative presentation on QSAR model development from small data sets. So can I take one question?
Yes.
So the question is that, can we apply QSAR modeling generation for different derivatives? How much it affects the quality of data?
Different derivative means, say, if you have a particular core and if you have different substituents on that, that is the classical type of set. Obviously, one can use QSAR. QSAR is for applying statistical analysis for a set of data differing in structural patterns. So obviously, this will be derivatives. So I think the question has been asked to know how much structural diversity can be tolerated. Now, it can be tolerated, but if some of the compounds are too much different from rest of the compounds, then one should omit those compounds. That means the outlier should be omitted. If there is sufficient structural representation in your set for a particular feature, then obviously those can be included in your QSAR model. But for each feature, there should be sufficient representation in the data set, and the number of compounds should be sufficient, number of descriptors should be low, unless you are using some machine learning techniques. For classical type of analysis, we use more number of compounds and less number of descriptors. And as I mentioned, that one should see if there is an outlier that should be removed. There may be one or two compounds having some particular feature that is not present in rest of the compounds, then one should omit those compounds. Otherwise, one will always use derivatives only, derivatives of structural congeners or similar compounds. And if you are doing 3D QSAR, then it can tolerate more degree of structural diversity and complexity. because in that case, you can consider your QSAR as feature based. That means what are the features you are considering, like hydrophobic or hydrogen bond donor, hydrogen bond acceptor, aromatic, and ionizable, etc. So, or in case of pharmacophore analysis also, you can consider this kind of features. So it depends on which kind of analysis you are doing, and depending on that, you have to consider a particular set for QSAR, or you may have to omit also some data set, because if you have a very small range of response values, or if there is no sufficient structural diversity in your data set, there is only a homologous is so simple a number of carbon atom can give you the good regression. Then in that case, there is no question of applying some descriptor. So that one has to decide. You have to see the data set, what is the diversity, what is the response range, whether a particular compound is having response that is quite different from others or not. And considering all this aspect, one should consider or select the descriptors for a particular model generation, and one should consider particular modeling strategy also for QSAR model development.
Okay, thank you, sir, for answering this question. So on behalf of Dr. G. Narendra Shastri, Director, CSR NIST and DDH Training Program team, I would like to thank you for accepting our invitation and gave presentation on this platform. Thank you, sir.
I have also enjoyed giving lectures, and especially I'm very pleased to be involved in the training program of drug discovery hackathon. I think the participants will be much benefited from this training program, and not only participants, I think other viewers also who are interested in QSAR or drug discovery programs, they will be benefited. Thank you.
Yes. These videos are available on YouTube also, so participants or other students also can see at any time. So it will be very good treasure for all the students and all the community. Okay, thank you, sir. So today's session will be closed here, and I request all the participants to join on Vertical 2 at 4 p.m. Okay. Thank you, sir.